Hello everyone, it's Dr. C. Happy Friday. I hope you're enjoying the snow. It's still coming down out there, although I guess the storm's almost done. But just think you can say you were in Flagstaff for the one-day record snowfall, at least, in recorded history that we know. So anyway, pretty cool. All right. Well, we missed class yesterday, so this lecture, which actually is a pre-lecture now, makes up for that lecture. This will not be as long as our normal lectures, but it'll certainly be longer than a typical pre-lecture because we do have to make sure we stay on pace for what we do need to cover this semester. So what we're going to do is we're going to wrap up the handout that we started in class on Tuesday. I'll also do some notes as well. So let's go ahead and wrap up problem 2. Then I'll go back to some notes for a while, and then we'll wrap up the rest of the handout. So this is the calculation we finished up with on Tuesday. So take a look at the general form of the equilibrium constant expression. It's the equilibrium constant, and we'll talk about an equilibrium constant called Kp in a little bit. But again, the C stands for concentration, so we're plugging in molarities. It's concentrations of the products, in this case just one product, raised to the power of the coefficient, divided by the concentrations of each reactant raised to the power of the coefficients. So that's always the form of the equilibrium constant expression. Since you were told in problem 2 that these are equilibrium concentrations, so read this carefully, we can plug those directly in and solve for the equilibrium constant. Okay. Now, another thing to point out here, you'll notice temperature is given. If you were in class on Tuesday, we came up with the equilibrium constant expression from the rate law, which had rate constant in it. So remember, the rate constant is a constant at a given temperature. Same thing for equilibrium constant, since it comes from a form of the rate law. Okay? So that's why temperature is there. It's not in the calculation per se, but this is the equilibrium constant at that temperature. If we change the temperature, the position of the equilibrium will shift and we will get a different equilibrium constant. All right, let's keep going with this one. So let's go down to B, and let me give myself a little bit of space here. So you might already notice that this reaction is the reverse of the original reaction we started with in problem 2a. But let's go ahead and set it up as if we didn't know that, and then see how things are related. So let's call this equilibrium constant Kc prime, just to note that it's different than our original. Again, products, in this case nitrogen, raised to the power of coefficient 1, times hydrogen raised to its coefficient 3, divided by reactants, in this case one reactant, ammonia raised to the power of its coefficient. And if we plug in the same values, nitrogen is 0.85 molar. Oh, remind me, that's so weird. I actually thought that, like you're here with me. Remind me to talk about units in just a second, but I'll remind myself. Okay, so let's just do this calculation and then we will compare. All right, so I ended up with, to 2 sig figs, I have 2.64 times 10 to the negative fifth. We only have 2 sig figs, so 2.6 times 10 to the negative fifth. Okay, so we could certainly solve this problem this way. Plug in our equilibrium concentrations again and solve. Now, there's a quicker way to do it by noticing how this equilibrium constant, K prime, relates to our original one that we just have labeled Kc. All right, and you will notice, or take a look here, in the first K, our reactants, our N2 and H2 are in the denominator. Since we reverse the direction of the reaction, now they're in the numerator. And what was in our numerator is now in the denominator. Okay? So by reversing the direction of the reaction, we have switched our reactants and products, and hence we have switched our numerator and denominator. We have inverted those, or done the reciprocal of that. So this new K, oops, well that's interesting. Let's just get rid of that. This new equilibrium constant, since our numerator and denominator have essentially flipped, is the inverse or the reciprocal of the original. Okay? And so we could have more easily calculated this. Now again, we're looking at a sig fig issue here. We'll see if this actually comes out the same because we rounded this first number. But this new equilibrium constant, K prime, is just the inverse. Reverse the direction of the reaction. Our equilibrium constant is the inverse of the original. And we do end up with the same answer, 2.6 times 10 to the negative fifth. Okay, so double check that. Okay, so, but that's something you should know. Reversing the direction, the new equilibrium constant is the reciprocal or inverse. Okay? All right, let's keep cranking with this. Let's go to 2C. And if you were not in class on Tuesday, this handout will be posted in Blackboard, so you can get that there. All right. Now, let me write the original reaction that we started with in 2A. It was N2 plus 3H2 going to 2NH3. Okay? And if we wrote out our Kc for that, as we've already done, NH3 squared over N2 times H2 cubed. Now, as we did up above, we could plug in our equilibrium concentrations again into our new expression. But let's look for the relationship here. All right, so compare our original expression to this one. And compare this reaction to this one. So let's look at the reactions first. What is the difference between those two reactions? Yeah, this reaction is multiplied by 2 compared to the original. Multiplied by 2. All right. Now, does that mean we multiply the original equilibrium constant by 2? So look at how these are related, these expressions. Is it multiplied by 2? No, it's not, is it? Remember, it's raised to the power of the coefficients. And now our coefficients are all a factor of 2 larger, and we're raising to, to those coefficients. So what you should see is that this expression is the original, assuming I can get my pen to work. So I'm going to rewrite the original. Squared. Okay, so this, we multiplied the equation by a factor of 2. That shows up as an exponent because we raised to the power of the exponent, right? And so when you raise to a power, you multiply the exponent. So 2 times 2 is to the 4th, 2 times 3 is the 6th, and so on. All right. So the relationship here is that is the original constant raised to the power of what we multiplied the equation by. The equation was multiplied by 2. We raise that equilibrium constant to that power. So this is very simply 3.8 times 10 to the 4th squared. And again, there might be a little bit of a rounding error here since 3.8 times 10 to the 4th is rounded. But we end up with about 1.4, and it's my calculation 1.44 but 1.4 times 10 to the 9th to 2 sig figs. All right? So you can save yourself some time in calculations, and it's important that you know these relations, because I will test you specifically on these relations, without a calculation. How is this equilibrium constant related to the original? Well, it's the square of the original, so you need to know that. Now, you forgot to remind me to talk about units, and I just reminded myself. So let's go back up to A and B and compare our units here. In the first one, molarity squared in the numerator, molarity to the 4th in the denominator. So molarity squared, molarity times molarity cubed, molarity to the 4th. This one ends up molarity to the -2nd. Molarity to the -2nd. Compare it to part B. Molarity to the 4th in the numerator, molarity squared in the denominator. This one ends up molarity squared. All right, so they end up to be different. And there is a relationship there, as you can see, but molarity to the -2nd versus molarity squared. So there are units for the equilibrium constant, as you can clearly see. And for Kc, it's going to be some unit of molarity. But, as you can also see, the units of molarity depend on what the reaction is and what the balancing coefficients are and whatnot. So typically, this is the one time in this course that you can disregard units. Typically, we will write our equilibrium constants without units. Is that good news? Yeah, probably, I guess, so we don't have to think about it. But realize there are units there. It's just that because the units vary depending on the reaction, we just don't list them. All right? So in this, going back to 2C, we would just say the equilibrium constant's 1.4 times 10 to the 9th. All right. Now, before we do part D, let's go back to the notes, because we haven't talked about what Kp is, what the relation between Kp and Kc and all that. So let's do some notes for a while. So just to remind you kind of where we left off in the notes, we talked about the definitions of equilibrium. We came up with this equilibrium constant expression. So this is a nice slide that kind of puts the definitions of equilibrium in a picture, more or less. So we have our reaction here, where we are starting with hydrogen and iodine. So look in figure A. So we have concentrations of hydrogen and iodine. Our product is hydrogen iodide. So at the start, we don't have any product in this case. And we'll talk about that does not have to be the case. But that's how we kind of think of reactions. Start with reactants, no products to start. So as this reaction starts to run, you can see the reactants drop off in concentration. The products increase in concentration. The product increases in concentration. And eventually we reach a point where those concentrations are no longer changing with time. They are not equal. In this case, we ended up with more product than reactant. But we have some of both, right? We end up with reactant and we end up with product. All right? And they are no longer changing with time. All right, so that is one definition of equilibrium. The concentrations of reactants and products are no longer changing with time. The other definition is what? The rate of the forward reaction equals the rate of the reverse reaction. And because those two rates are equal, the concentrations are no longer changing. But again, you'll notice this word dynamic. This is a dynamic situation. Reactants are continuously going to products. Products are continuously coming back to reactants. They're just doing that at the same rate, so it appears that nothing's changing. Okay, so keep that in mind. Here's another reaction, and a lot of times I will show a video of this one, so I might do this in class on Tuesday. This is a nice equilibrium to follow because NO2 is a brown gas. Okay, it's a brown colored gas. N2O4, the reactant in this case, is colorless. So it's easy to see the position of this equilibrium change. If we have more NO2, our or say, we want to say solution, it really will be a solution. Solution of gases will be darker in color, darker brown. If we have more N2O4, our solution color will lighten up. Okay, and so it's an easy reaction to follow which way the equilibrium lies. All right, so we'll do that as we go on. It's a nice one to follow. Now, I wanted to show you this slide because it's going to take a little while for you to wrap your minds around this. We typically do start reactions with just reactants. So remember this reaction, we were showing N2O4 going to 2NO2. All right, so this is the situation we typically would think about. We're starting with reactant, no product, and over time our reactant concentration drops off, our product concentration increases, and then we reach equilibrium at this point. Concentrations of reactants and products are no longer changing with time. Again, note they are not equal. Okay, so equilibrium does not mean equal concentration. It means equal rate, and hence concentrations are no longer changing with time. So that's how we typically think about reactions. But that does not have to be the case. We could do the opposite. We could have our equilibrium written this way, and we could start with no reactant and start with only product. Because this is a reversible reaction. So if we start with just product, well, the reaction obviously will go to the left first, and then as we start building up reactant, it will come back to the right. All right, so reversible. So you will see reactions where you will be given a reaction and you will start with only product. That's okay. Okay, don't worry about that. If you start with only product, it has to go to the left. It has to go to reactants first. Now, a third situation is that we start with some of each. Why not? It's a reversible reaction. Okay, so if we start with some of each, we're still going to reach equilibrium. In this case, NO2 decreases, our product decreases, our reactant increases. Eventually, we reach equilibrium. Okay, so no matter where we start with only reactant, start with only product, start with a mixture of reactant and product, we will eventually reach equilibrium where the concentrations are no longer changing with time. All right, and if these are all run at the same temperature, when we plug in these concentrations that we end up with, we will get the same K if we're at the same T. We might have different concentrations at equilibrium, but when we plug those into our Kc expression, in this case NO2 squared over N2O4, if we're at the same temperature, we're going to get the same constant. It's a constant at a given temperature. All right, so think about that. You've already seen this. I don't typically call it the law of mass action. I think it makes more sense to call it the equilibrium constant expression, but it's also called the law of mass action. This equilibrium constant, products raised to the power of the coefficients, again, then they're multiplied together, divided by reactants raised to the power of the coefficients, again, multiplied together. All right, so we've already seen that. Now, this is something new, and we're going to get to something called Kp. And as you can see here, the P stands for pressure. So for gas phase reactions, everybody loves the ideal gas equation. All right, very nice, simple equation, works very well. And for our purposes, normal atmospheric conditions, room temperature, those are fairly ideal conditions for a gas. All right, well, if we rearrange this and divide by V, we end up with, in this equation, as you can see in the parentheses, P is equal to N over V times RT. N is moles, V is liters, volume in liters, moles divided by liter. Oh, look at that. And I wish, there's something weird that has started happening with my pen where it decides it really would rather be a mouse than a pen on its own somehow. So I apologize for that. So essentially you will see molarity is in the ideal gas equation. So for a gas, pressure is proportional to concentration, to molarity. So higher pressure under given conditions, more gas, more concentration of gas. Lower pressure under given conditions, lower concentration of gas. So for gases, we can plug in pressure in atmospheres. This would be, because it's the ideal gas equation, this will be in atmospheres, rather than molarity. So this will give us a new equilibrium constant, Kp. Now for this reaction that we just looked at, we would simply write it as pressure of NO2, products, raise the power of the coefficient, don't forget that, over pressure of N2O4, raise the power of the coefficient, which in this case is 1. All right, same form, products over reactants, raise the power of the coefficient. It's just a different unit of concentration, pressure rather than molarity. All right, so don't be confused by Kp. It's just using a different unit of concentration. Okay, so I already wrote that out. To distinguish, we will use a subscript of P rather than C for molarity, concentration. Now, you will see these called partial pressures because these will be mixtures of gases. Okay, and so if we had a mixture of these two gases, the total pressure in that mixture is the sum of the partial pressures of each gas. And we talked a little bit about that last semester. But don't worry about the term partial pressures. You will just plug in the pressure of each gas. All right, a couple more things before we get back to our handout. Magnitude of K, really important. Really try to wrap your mind around this. All right, the magnitude of K tells us a lot. All right, and I actually like this. A lot of students maybe have never seen this before. This means much greater than. Okay, so a double greater than sign. So what if our equilibrium constant is much greater than 1? Meaning, what if our equilibrium constant is really large in magnitude? All right, now, let's go back to Kc because we like molarity better, I think. And my pen just switched to mouse randomly. And it just did it again. I wonder what's going on here. Products, raised to the power of the coefficients, over reactants, raised to the power of the coefficients. So I will write a general form of the equilibrium constant expression quite often like this. All right, products raised to the power of the coefficients, over reactants raised to the power of the coefficients. So what if Kc is really large? Large in magnitude, big number. What does that mean? Well, look, and of course, sometimes when you have slides, you give away the answer too soon. But to end a big number, well, how do we get a big number? Numerator is going to be much larger than the denominator. Okay, much larger numerator than denominator to end up with a large magnitude number. All right. So what that means is that when that system reaches equilibrium, we're going to have a lot more product. That's what a large K tells you. And by large K, typically we're talking, 10 to the 5th, 10 to the 6th, or larger, maybe 10 to the 4th, but kind of in that magnitude. So a K that's like 10 to the positive 5th. We would say that's a large K. That means our equilibrium lies to the products. We're going to, once that system establishes equilibrium, once we get to a point where the concentrations are no longer changing with time, we're going to have a lot more product than reactant. That's what a large K tells you. Conversely, a small k, a k much less than 1, an equilibrium constant much less than 1, to get a very small k, small numerator, large denominator. Okay, so a small k tells us reactants are favored when equilibrium is established, or we would say the equilibrium lies to the left, it lies toward reactants. So that magnitude of K is really important, and we're going to come back to that in a calculation before this lecture is over. All right, and we're going to look at that magnitude of K and how it can help us in our calculations. All right, so for a really small K, typically, small Kc, we're looking in the 10 to the negative fifth kind of range. 10 to the negative fourth is kind of borderline, but we'll talk more about that when we look at some reactions with small k's. So large K, mostly products at equilibrium. Equilibrium lies to the right. Very small K, reactants are favored. The equilibrium lies to the left. It's important that you know that because we'll keep coming back to that. All right. So here's just a visual example, which kind of helps. This would represent the system at equilibrium. And if you look at what your products are and what your reactants are, you can see mostly product. All of this is product that I've circled. There is some reactant, so at equilibrium we will have both, but in this case we end up with mostly product, very little reactant. So we're going to end up with a large K. Mostly product at equilibrium. Large numerator, small denominator, you're going to get a large number. Okay, here's another one. This one, if you look at everything except for those two guys, this is all reactant at equilibrium. Okay, so small numerator, large denominator, small k. Equilibrium lies to the left. And that was supposed to be an arrow. Wow, that was good. Okay, so we would say reactants are favored at equilibrium, equilibrium lies to left, something like that to indicate the position of equilibrium. So to review, just take a pause for a second. Please remember, equilibrium does not mean equal concentration. Lock that away somewhere. Okay? It's a common misconception, and it's a terrible common misconception. Equilibrium does not mean equal concentration. It means equal rate. But the equilibrium position will vary depending on the reaction. Some equilibria will lie far to the right, product favored. Some equilibria will lie far to the left, reactant favored. The magnitude of K will tell us which way. Some equilibrium will be more toward the middle, but it varies depending on what the reaction is. All right? Equilibrium means equal rate. Concentrations are no longer changing. All right, keep that in mind. All right, a couple more things before we crank out some calculations. So far, we've only talked about gases, and those certainly show up in the expression. All right, but what about solids and liquids? Okay, so solids and liquids are a little bit different. The concentration of a solid does not depend on how much is present. So think about that for a second. And I think the easiest way to think about that is in terms of density. Okay? So a solid is going to have a certain density. Whether we have a lot of the solid or a little of the solid, it has the same density. And density is really a concentration. How much per volume? Concentration. So what happens here is that this solid, and my concentration is really constant. The amount per volume, even though the total amount will change in the course of that reaction, its concentration does not. Its amount per volume stays the same. So it's a constant, and we can combine it with this constant that I've labeled K prime, and we can end up with our typical K. So constant times a constant is another constant. And we only include the gases in our expression. Okay? Products over reactants, and we only include the gases, raise the power of the coefficients, both 1 in this case. All right, so we don't include solids. We'll find the same thing for liquids. All right? Even though the amount of the liquid will change, its concentration does not. Picture sometimes helps. This reaction certainly is going in a certain direction, right? If you look at this, we're actually making more product, so this, as this reaction runs, is going to the right. We are making more carbon dioxide, and we are making more carbon, but the concentration of that solid hasn't changed. Yes, we have more mass, but we have more volume. Mass divided by volume is going to be the same compared to the mass divided by the volume over here. So we don't include solids, pure liquids in our expression. So this one would just be, depending on whether we're using, why don't we write this one as Kp? This would be pressure of CO2 to the first over pressure of CO, coefficient 2 squared. And we would not include the solid in our expression. We could also write a Kc expression for that as well. All right, and I think the last thing before we actually finally get back to our handout. I'm not going to derive this now. I don't really think it's worth our time. But we did see in the ideal gas equation that pressure is directly proportional to molarity. All right, so pressure is proportional to molarity. And you can see there's this RT factor in there, which you now see here. R is 0.0821. There's our temperature. Okay, so there is a simple relation where if we have the Kc value, we can actually get the Kp value for that reaction. All right, and vice versa. All right, and so here's the equation. Kp is equal to Kc. Here's the RT, 0.0821 times T. Now here's something that's going to depend on how much gas is present. How many moles of gas product minus how many moles of gas reactant. Remember, it's only the gases that are going into the expression, not solids or liquids. So we only focus on the moles of gas. Okay? So there is one occasion when Kp will equal to Kc. When is that? Yeah, when our delta N is equal to 0. So if we have the same number of moles of gas product, same number of moles of gas reactant, our delta N is 0, and this 0.0821 T to the 0th power is just 1, and Kp will equal to Kc. Okay? Otherwise, if there's a difference in number of moles of gas product reactant, Kp will not equal Kc. So in general, we would say probably more often than not, Kp does not equal to Kc. They're only equal if the change in moles of gas is 0 in the reaction. All right, I think that's all the notes I need to do here. Yes. So let's go back to our handout. So this problem, and let's scroll back up and look at what we have. The long way to solve part D, where we want the Kp value, would be to go back up. We have the molarities. We know the gas constant. We know the temperature. And as we saw, pressure is mRT. Okay? We could plug in and get the pressures of each of these gases at equilibrium and solve for Kp that way. Once we had each pressure, we'd plug into the Kp expression. That would certainly be one way that we could do this problem. Be a little bit longer because I'd have to get the pressure of ammonia, the pressure of nitrogen, the pressure of hydrogen, and then solve for Kp. But as we just saw, Kp is equal to Kc, RT, 0.0821 times T, delta N. Okay, so in this case, we have our Kc for this reaction from problem 2a, which actually still happens to be written right there. 3.8 times 10 to the 4th, 0.0821. What's our temperature? 127. Add that to 273, 400 Kelvin. Remember Kelvin by default. And then what's our delta N? Yeah, final minus initial. Remember, a delta is final minus initial, products minus reactants. 2 moles of gas product 4 moles of gas reactant, delta N is 2 minus 4, which is a negative 2. All right. So again, it's just the RT that's raised to the negative second, not the Kc value. So you have to do, I would do the RT to the negative second first. So 0.0821 times 400, raise that to the negative second power. All right, so when you do this, you should get 9.27 times 10 to the negative fourth for RT to the negative second. Now we have to multiply that by 3.8 times 10 to the fourth. And for this one, my Kp ends up to be 35-ish, 35.2. But we only have 2 sig figs. All right, so note, Kp does not equal to Kc. They're only equal if delta N is 0, and it's not 0. So our Kp and Kc will be different values at the same temperature. Okay, so make a note of that. All right, so we will use both. We will use Kc, we will use Kp. So get used to using both values. Now, if you do have a Kp value, you have to plug in pressure and atmospheres. If you have a Kc value, the equilibrium amounts will be molarity. All right, let's keep going. All right, so I think there's 2 more problems on this handout. Is that correct? Oh no, there's more than that. All right, so problem 3. Let's do this one. I was thinking I was on to problem 4 already in my mind, and obviously we're not there. Let's read through this one. We are given an equilibrium constant. Now, if it doesn't say which one it is, if you're given molarity, assume that this is the Kc value. And I should try to do a better job in some of my problems to say that that actually is Kc. Because if that was K, well, in this case, it wouldn't matter, right? Look at our delta N. 2 moles of gas product, 2 moles of gas reactant. Hey, how about that? In this case, I don't have to specify whether it's Kp or Kc, because they'd be the same. That was kind of fortuitous. But generally, if there's still the case where you're given a K value, assume it's for whatever unit you're using. All right. So in this case, reading this carefully, it tells you you are at equilibrium. That's important. When it's analyzed at equilibrium, these are the concentrations of H2 and F2. What's the concentration of HF at equilibrium? All right. So this one looks pretty straightforward. In this case, we have the K value. We're solving for one concentration. So starting with our Kc, products to the power of the coefficient over reactants multiplied together to the power of the coefficients. In this case, we are given Kc, we are given H2 and F2 concentrations at equilibrium. What is the concentration of HF? All right, so let's plug in. All right, so both concentrations of H2 and F2 are 0.0021 molar. So I end up with here HF squared, be careful, is 9.26 times 10 to the negative third. Okay. Now, that is not the concentration of HF at equilibrium. That's the concentration of HF squared. So what do we need to do mathematically to get the concentration of HF? Yeah, we need to take the square root of both sides. All right, so the square root of HF squared will just be HF. Square root of 9.26 times 10 to the negative third will give us the concentration of HF at equilibrium. I'm not going to finish this. I think you can take the square root. You'll probably see this on the quiz. Okay, so take the square root of that. Make sure you can get the correct answer for this. Okay? Now, one nice thing on a lot of these equilibrium problems is you can check your work. Once you do get a concentration for HF, plug it back in. Plug in your HF concentration. You have your other ones. Do a quick calculation and see if you get that equilibrium constant. If you do, probably solved it correctly. But if you plug in your HF and you don't get that equilibrium constant, you did not solve the problem correctly. So you can check these quickly sometimes. Okay, now we're going to spend a lot of time doing calculations like the ones you're going to see in the next 20 minutes. And I think that will get us to about an hour's worth of lecture. Yes, I know. Thanks for hanging with me. I know this is probably pretty painful listening to Dr. C talk for an hour. But we do have to make up for class, and this will actually be a little bit shorter than the class period. So, first thing in problem 4, note the magnitude of K. So, back in the lecture notes not that long ago, I talked about how important it was to understand what the magnitude of that equilibrium constant tells you. Small k, what does that tell you? Is that a product-favored reaction or a reactant-favored equilibrium? Yeah, small k, reactants are favored at equilibrium. So make sure you can look at the magnitude of K and know product-favored or reactant-favored. Small k, reactants are favored at equilibrium. We will have mostly reactant at equilibrium. That becomes important when we go to set up this problem. Now, a couple other key things to note as you're reading through this problem. You have that many moles of CO2 initially is placed in a 5-liter vessel, 5-liter container. Calculate equilibrium concentrations of all species. All right. Now, it does not say equilibrium, and it doesn't say anything about carbon monoxide or O2, so we don't even know what those are. And we actually do. They're actually 0, and we'll talk about that. So this one, we're starting off with initial amounts. We are certainly not at equilibrium. So these problems are significantly more difficult than the ones we've looked at so far, because we can't just plug into our equilibrium constant expression because we're not at equilibrium yet. Okay, so make sure you notice that. So this is going to take more work. So here's our reaction. And so I'm going to write out initial. And since we're given Kc, we're working with molarity, so initial molarity. Well, what's my initial molarity of CO2? 2 moles in a 5-liter vessel. Moles divided by liters. So our initial molarity, there's my pen wanting to be a mouse over and over again. Hope we only have 2 sig figs. 0.4 molar. Now you will notice it just says you put CO2 in the reaction container, reaction vessel. Doesn't say anything about CO, doesn't say anything about O2. Those are 0. All right. Now, right away, when you see a 0 in a reaction like this, you know you're not at equilibrium. Even though this is reactant favored, we will have some product at equilibrium. At equilibrium, you'll have some reactant, some product. This one, we're going to have a lot more reactant, very little product. But we'll have some of both. So anytime you see a 0, straight away you know you're not at equilibrium. All right. Now, clearly, there has to be some change for this system to reach equilibrium. We have to produce a little bit of product. Again, this reaction is going to lie far to the left, but we will produce some product. Now, how much? Yeah, we don't really know. We're going to have to figure that out. So we know some of our reactant is going to react. So we're going to put a negative here saying that the amount of reactant is going to decrease. It's going to go to product. Now how much? Well, we're going to base it on the coefficient. I'm going to use that coefficient. I am so sorry. I've got to figure out, and this is a very recent with my stylus. It's just decided it's just going to randomly jump and become a mouse whenever it feels like. So negative, the amount of reactant is decreasing. We're going to produce some product. We're going to factor in the coefficient. We don't know how much is going to react, so we're going to have to figure that out. So we're going to use a variable, and x is the common one that's used. So let's call this negative 2x. Okay? So if negative 2x reacts, how much carbon monoxide will I produce? Because we're going to produce product. It was 0. We have to make some product. Well, it also has a coefficient of 2. X. So if 2x of CO2 reacts, we're going to make 2x of CO. What about O2? Yeah, O2 has a coefficient of 1. So for every 2 CO molecules, carbon monoxide, we produce, we're only going to produce 1 O2 molecule. And at equilibrium, 0.4 minus 2x for our CO2, 0 plus 2x, 2x for CO, x for O2. All right, so take a look at that table very quickly and try to wrap your mind around it. Okay. First, we just start with the initial amount, so we know we're not at equilibrium. We know this system has to shift to the right. Even though we know based on the magnitude of K that we're not going to have much product at equilibrium, we're going to have some. Okay. So it has to go from reactant. Reactant is going to decrease and produce product. That's why it's negative positive. And the amount that reacts and is produced is going to be based on the coefficients. And then to get the equilibrium amounts, we just sum those together. All right. Now, you do know how to write the form of the equilibrium constant expression. Kc, products, power of the coefficient, over reactants, power of the coefficient. Okay, so we can plug in Kc value, I think was 2 times 10 to the negative 6. It scrolled off the screen, yeah. And then just plug in our equilibrium amounts in terms of x. CO is 2x squared. O2 is x. CO2 is 0.4 minus 2x. And again, don't forget the raised to the power of the coefficient squared. So what you will notice, you actually see the coefficients in this case of 2 twice. You see them in the x term, 2x, and you see it in the squared term. Okay, so be careful. You're going to see that coefficient 2 different times. We actually see this coefficient of 1x, raised to the first power as well. All right. Now, some of you have graphing calculators, and this is another reason why, and we might have to not allow graphing calculators on the next exam, because I do not want you to use your graphing calculator to solve this. We are actually going to end up with a cubic equation here, because our numerator, 2x squared, 2 squared is 4, 4x squared times x. We're going to end up with a 4x cubed term in the numerator, and then we're going to end up with a quadratic equation in the denominator. So we're going to end up with a cubic equation. If you have a graphing calculator, a graphing calculator can solve a cubic equation. Okay? Scientific calculator cannot, typically. All right? So the point here is I want you to be able to solve this without using a calculator, at least at this point. And the way we're going to do this is we're going to make a very, very, very important assumption. So let's scroll back up to our table. We know the magnitude of K. We know it's really small. reactants are favored at equilibrium, meaning that when we do get to equilibrium, we're going to have almost all reactant, almost no product. Okay, and that's why the magnitude of K is hugely important. So what that means is that this amount that we have as 2x is going to be very small. Okay, we know some reactant's going to go to product, but not much. Not much. So that 2x term is going to be really small. How do I know that? The magnitude of K. Really small K, mostly reactant at equilibrium, very little product. So the amount of reactant that goes to product is really small. And it's so small, we're going to assume, and again, we're making an assumption here that's going to simplify our calculation. We're going to assume it's small enough that 0.4 minus a really small number is going to stay approximately 0.4. Let me write that in black. So key assumption for us, we're going to use this a lot because even when we get to the next couple of chapters, we're going to look at reactions, acid-base, precipitation, where our K values are really small. And we're going to make this assumption over and over and over again. When we have a very small K, reactants are favored, the amount of reactant that goes to product is going to be really small, and we're going to make an assumption that it's so small, in fact, that the initial minus that really small number is going to stay about the initial. Now, we know it's going to drop a little bit, but again, we're making a simplifying assumption so that it makes it easier for us to solve this problem. So, how does that change this? Well, that 0.4 minus 2x now, we're going to say is approximately 0.4. So instead of 0.4 minus 2x, we're just going to plug in 0.4 there. All right, so now our math becomes much simpler. We still have our K value. We still have 4x cubed in the numerator. But now our denominator is 0.4 squared. We still have this squared term, so don't forget about that. Wow. Say wow. That equation is much simpler. Okay, because now all we have to do is go 0.4 squared times our K value. So let's do that. So 2 times 10 to the negative 6th. Oops, I did not punch that in my calculator correctly. Multiplied by 0.4 squared. All right, so this is 4x cubed. I'm going to write it on the left-hand side now. But our K value times 0.4 squared, we had 3.2 times 10 to the negative 7th. Okay. Now divide by 4. Come over here. X cubed is equal to 8 times 10 to the negative 8. All right, almost there. Now we just have an x cubed term to take care of. So what do we have to do here? Yeah, the cube root. So a lot of calculators have a cube root key. If you do not, on yours, mine actually does not. Cube root is the same as raising to the 1/3 power. Okay, so 1/3 power, 0.33333. So you could raise it to that power. And you should get an x value here of 4.3, and I'm going to carry an extra sig fig here, times 10 to the negative 3rd. And what's my unit? And I know your first thought was probably, well, there are no units. For K, we don't include units. But this is not K. This is X. These are concentrations of the species in that equilibrium. So this is molarity. If we were using Kp, it would be pressure in atmospheres. Okay, so watch for that. All right, are we done? We are not done with this problem. Okay, so The question was, what are the equilibrium concentrations of everything in that reaction? What are the equilibrium concentrations of everything in that reaction? All right, now, we've solved for X. So we do have the equilibrium concentration of O2. So this is equal to the O2 concentration at equilibrium. But what is the concentration of CO? Yeah, and I'm sorry, my table is really mucked up here right now. But concentration of CO is 2x. So if you want the concentration of CO, all you do is have to take 2 times x. All right? I'm not going to do that for you because you might see that in the quiz. I think you can do that. All right. Now, let's actually see if our initial concentration didn't change very much. So what is the concentration of our reactant CO2 at equilibrium? Yeah, it's 0.4 minus 2x. Now we assume that stayed about 0.4. Well, let's see if that is indeed the case. CO2, sorry, is 0.4 minus 2x. So 2 times your x value, subtracted from 0.4, and let's see what we get. And to 2 sig figs, I end up with 0.39 molar. Did it change much? No, and that's what we expected, right? Because of the small magnitude of K, that tells us at equilibrium, almost all reactant. Look at our product amount. Product amount is small. That's the amount of O2, 0.00431, compared to our amount of reactant, which is much larger. Mostly reactant at equilibrium. We assumed that because our K was so small that our reactant amount wasn't going to change very much. And indeed, that's the case. In class on Tuesday, remind me, there is a very important check that we should do right now to see, indeed, was this 2x term small enough to make the assumption that we made. I don't want to do that right now because I'm kind of running out of time here and I want to at least set up the next problem. But remind me, we want to check our assumption. Okay, so someone yell at me in class on Tuesday and say, Dr. C, we need to check our assumption on problem 4. Okay, is that assumption valid? In this case it is, but we should double check it. All right, last thing for today. I don't think I'll finish this one, and you don't have this problem 3. I have kind of some handouts blended together here. So this, let's get rid of that. That's not even in your handout. This is the last problem in the handout, I believe. Let's at least set this up. Oh, one last point about problem 4. We affectionately call these tables that we set up here, this table with initial and change in equilibrium, we call these ICE tables. And you might have heard that in high school. But ICE doesn't have to do with water. It has to do with initial, change, equilibrium. So ICE table. And we'll talk more about that as we go on. All right, last thing for today. Let's set this one up. Now, a couple things to note here. You're given a Kp value. That should not bother you because all that means is you're going to be using pressure atmospheres. Everything else is the same in terms of how we set this up. All right, here we go again. Initial pressure. You're not given equilibrium pressures. And actually, you're just giving the initial pressure of NO, which happens to be a product. So I wanted to set this one up just to show you we can start an equilibrium with only product. Okay? That should not bother you because it's a reversible reaction. We can go in the reverse direction first. All right, so let's do that. Okay, ICE table, initial. Nothing is said about N2 and O2. It just says you start with initial pressure of NO of 0.8 atmospheres. Okay, that's it. Now, is the system at equilibrium? say no. No, it's not at equilibrium. Anytime you see a 0, you are not at equilibrium. Okay? This K is, not super small. Does mean we're going to have probably a little more reactant at equilibrium than product. All right? We're certainly going to have reactant. And the fact that these are 0 right away, we're not at equilibrium. Now, this is where this is going to seem a little odd because we're starting with product and no reactant. This reaction initially has to go in reverse. It has to go to the left. It can't go to the right. There's no reactant to react. So our product has to decrease. Okay, again, negative sign. Amount of product is going to decrease. We use the coefficients. And we are going to, in this case, produce reactant. Again, using our coefficients. For every 2 NO molecules that react, we're going to get 1 N2 and 1 O2. And at equilibrium, X, X, and 0.8 minus 2X. Okay? Now, at least let's plug this in, and we're not going to solve this. We are working with Kp this time. Pressure of NO, product, raise the power of the coefficient. Pressure of N2 times pressure of O2. Okay? Plug in. Kp was 0.05. NO is 0.8 minus 2x squared. And our reactants are x times x, so we have x squared in the denominator. All right. I'm going to stop here, but I just want to mention how we could solve this. And we will do this at times. We're going to end up with a quadratic equation here. Okay? So I do expect you to know how to solve a quadratic equation, and we will practice some of these. Okay, how do we solve a quadratic? Now, this one, though, there is another way we can simplify this so we don't have to solve a quadratic. And it's not the assumption that we made in problem 4. Okay? The assumption in problem 4 was based on the magnitude of K. This K is not small enough to make any kind of assumption. Plus, we don't have an initial amount of reactant. It's just not going to work here. So this is not an assumption. This is just a simplifying math calculation. You will note that there is a squared term in the numerator and a squared term in the denominator. If you see something like that, which you will see sometimes in these problems, you can quickly simplify this by taking the square root of both sides. Since this is a squared term, the square root of that will just be what's in the parentheses. The square root of x squared is just x. Okay? So you might want to try to finish this one. I'm not going to put this one in the quiz, but you might want to just try to finish this one, taking the square root of both sides of the equation to simplify this down to solve for x. All right, and we will wrap this one up in class on Tuesday. All right, so these ice table problems, you're going to see a lot of these this semester because you're going to see them in this chapter. When we get into the acid-base chapter next, a lot of that is equilibrium, where you'll see ice tables. The next chapter has buffers and solubility. You'll see ice tables again. So really work to understand what we're doing in these ice tables and why we're setting them up the way we are. Again, we're not given equilibrium amounts, so we have to start with initial. We know we're not at equilibrium. We know which way this system has to shift. We get equilibrium amounts in terms of x, and we have to solve for these x values to figure out what we do have at equilibrium. Okay? Not easy, but we'll practice lots of these. All right? So this gets us started on it. Watch for the pre-lecture quiz that'll be based on all of this stuff, and we will review more ice table stuff in class Tuesday. All right. I will see you soon. Enjoy the snow. Stay safe out there. And and don't forget, and I will send out an announcement, we also do have the retest Monday night. So I will be sending out more information about the retest Monday night as well. All right, I will see you hopefully sometime early next week. Take care.